Welcome to ScienceCover.com. In this session, we look at longitudinal and transverse waves. The aims of the session are to know what we mean by a wave, to describe and give examples of a longitudinal wave, and describe and give examples of a transverse wave. First, pause the video and complete the Do Now task. Let's check our answers. We can see the locations of the hidden words on the screen now. To begin, let's explore what we mean when we talk about a wave. A wave moves energy from one place to another without the movement of matter. For example, a sound wave. Vibrations cause the particles to move forward. These bump into their neighbouring particles and pass on the vibrations. These particles then move and bump into their neighbouring particles. And in this way, the vibration or energy is passed on. But the particles, the matter, do not move too far. Light waves are made from electric and magnetic fields. The energy moves as the field changes location, but there is no light particle. Water waves draw up water from in front of them to replace water being left behind them. In this way, the wave moves energy over the surface, but the particles don't move too far. Both these are examples of waves, as they're moving energy from one location to another, but not moving matter. This table shows some different types of waves. We know that a sound wave is a wave that carries energy from a vibrating source through the air. We've mentioned that a light wave has electric and magnetic fields carrying energy through space. Water waves, they are created when the wind blows over the surface of the water, causing vibrations and movement of the surface water. Then we have P waves and S waves. These are two types of waves created during earthquakes. Pause the video now and complete task 1. Let's check our answers. Number 1, complete the sentence to define a wave. A wave transfers energy from one place to another without the movement of matter. Question 2, match the type of wave to its description. A light wave is the electric and magnetic fields carrying energy through space. A sound wave is a wave carrying the energy from a vibrating source through the air. A water wave is where the wind blows over the surface of water, causing it to vibrate. And the P waves and the S waves are both waves created during an earthquake. Let's now move on to look at longitudinal waves. All waves can be categorized into two types: longitudinal waves and transverse waves. A longitudinal wave is where the direction of the vibrations is in the same plane or the same direction as the wave movement. So in this diagram, we can see that the speaker is vibrating right to left, and this is creating waves that are moving to the right. Since they're moving in the same direction as the vibrations, this is a longitudinal wave. Longitudinal waves can often be identified as they create compressions. The areas that are not compressed are known as rarefactions. Some of the characteristics of a longitudinal wave are on the screen now. We know that as a longitudinal wave moves through a medium, the particles of that medium are moved back and forth by the waves. One back and forth movement is called one oscillation. Oscillations of the particles will be in the same direction as the wave movement for a longitudinal wave. And this will create a region of compression where particles are close together, and a region of rarefaction where the particles are far apart. Some examples of longitudinal waves are sound waves, compressions moving down a spring or slinky, and P waves from an earthquake. Pause the video now and complete task 2. Let's check our answers. Number 1, what is a longitudinal wave? This is a wave where the vibrations are in the same direction as the wave travels. Number 2, give examples of a longitudinal wave. It could be a sound wave, compressions moving down a slinky, or P waves from an earthquake. Place the labels on the correct arrows. The speaker will be producing vibrations. The blue arrow is showing us the direction of the wave. Then we have two areas, one where the waves are close together, this is a compression, and one where the waves are spread out, this is a rarefaction. Now let's look at transverse waves. We've said that all waves can be categorized into two types: longitudinal waves and transverse waves. A transverse wave is where the direction of the vibration is at a right angle or 90 degrees to the wave movement. We can see this on the screen now. In this diagram, the vibrations are moving the wave up and down. This creates a crest and a trough. But the direction of travel of the wave is at 90 degrees to this, and the wave moves left to right. We can see some of the characteristics of a transverse wave on the screen now. We know that the waves will move up or down, or perhaps right to left, and one up and down movement, or right to left movement, is called one oscillation. The oscillations of the particles are at right angles to the direction of the travel. A crest is the maximum displacement of the particle above the equilibrium position, and a trough is the maximum displacement of the particle below the equilibrium position. And the crest and the trough should be equal in size. Some examples of transverse waves are light waves, a side-to-side motion of a spring or a slinky, and the S waves from an earthquake. Pause the video and attempt task 3. Let's check our answers. Number 1, what is a transverse wave? This is a wave where the vibrations are at right angles to the direction of motion. Give two examples of a transverse wave: a light wave, a water wave, or an S wave. Question 3. Add labels to the correct position on the diagram. The crest is the highest point of the wave, the trough is the lowest point of the wave. The vibrations are represented by the green arrow travelling up and down, and the direction of the wave is represented by the blue arrow moving left to right. We can use a slinky to model how longitudinal waves transfer energy. If we move the spring, vibrating it forward and backwards, this creates compressions. The compressions move down the spring, transmitting the energy, but the material of the spring only vibrates around a fixed point. A sound wave works in a similar manner. A vibration pushes air particles back and forth. These bump into neighbouring particles and pass on the energy, but the particles of air stay around the same location. In this way, sound energy can spread outward from a source. A slinky can be used to model a transverse wave. If we move the spring left to right or up and down, this creates waves in the spring. These waves move down the spring at a right angle to the direction of the vibrations. Light waves and water waves are both examples of transverse waves. After an earthquake, two types of wave travel through the earth. A P wave is longitudinal and will shake the ground up and down. An S wave is transverse and shakes the ground side to side. S waves cannot pass through liquids, whereas P waves can. We know S waves do not pass through the Earth's outer core, and this is evidence that the Earth's outer core is a liquid. Pause the video and complete task 4. Let's check our answers. Number 1. When a sound wave passes through the air, describe what happens to the air particles. An air particle is pushed forward by a vibrating source. This strikes a neighbouring particle and passes on its kinetic energy. The neighbouring particle then moves and strikes another neighbouring particle. Through this mechanism, the energy is passed from particle to particle and spreads out. We see compressions in the air, we see rarefactions. Question 2. A student lays a skipping rope out on a straight line on the floor. They go to one end of the rope and then vibrate the handle left to right. This sends waves down the rope. Are the waves longitudinal or transverse? It will be transverse. Part B. Describe the direction that energy is moving down the rope. The energy will be moving along the rope away from the student. Part C. Describe the movement of the rope, left to right or side to side. Question 3. Explain how you could use a slinky spring to create a transverse wave. Stretch the spring outright and vibrate the end of the spring up and down or left to right. Part B. How could you use it to create a longitudinal wave? Stretch the spring outright and vibrate the end of the spring forward and backward. Question 4. Earthquakes produce P waves and S waves. Describe the difference between the two waves. P waves are longitudinal, whereas S waves are transverse. P waves shake up and down, whereas S waves swing side to side. P waves can travel through a liquid, S waves cannot. Part 2. Explain how they supply evidence that the outer core of the Earth is a liquid. We know that P waves can travel through a liquid, whereas S waves cannot. P waves can travel through the outer core of the Earth, but S waves cannot. This suggests that the outer core of the Earth must be a liquid.